Hello everyone and welcome to the third part in the SpriteKit tutorial series. And we are going to be building upon the project that we created in part 1 and part 2. So if you haven't already, go ahead and watch these so that you can keep up and you know where we're at. Just a quick recap. We made a scene with an SK node label here, and when we click the scene, we had a door transition here to another scene, and then we have the spaceship that runs a series of actions that moves it around. And what we're going to do now is very interesting. We're actually going to make physics. We are going to apply physics to this small spaceship game or spaceship example. So let's just go ahead and do that. And in order to do that, it's actually very simple and extremely easy to add physics once you've created your sprite nodes. And if you go into, let me just increase the text size. 20, yeah, 22 maybe. Yeah, alright, so go into the new spaceship methods, and this is where we made the spaceship hull, and we made some actions. We created 2 lights by using the new light method. We don't want to simulate physics on these lights because they are a child node to the spaceship. So we just want physics to be applied to the hull itself, which is actually the entire spaceship. And just going to say add physics here. In order to do that, we simply just say hull dot physics body equals to sk physics body class, body with rectangle of size hull dot size. And what we're doing here is that we are actually making a physics body. Each sprite node has a physics body property, and that physics body property, it takes or it can hold an SK physics body object. So we make one of these, and we make a body with a rectangle of size, hull dot size, meaning that we want the physics body of this particular sprite node to be the entire node. You could have it just be half the node, and then physics would only be applied to half the node. So that's actually it. With this single line of code, we actually made physics. And let's just see how that looks. If we go ahead and run this, and as soon as the doors open, you can see our spaceship just crashes. It plummets to the ground because that is the gravitational pull. It will pull everything down, and since there's nothing to collide with our spaceship, it just keeps on falling down. There's no ground or anything. It's like an empty earth. There's just a gravitational pull that pulls all the nodes down until they simply disappear. And that's not very useful in our example, but it shows how easy it is to make physics. And with physics also comes collision detection, which is something we're going to take a look at. But first we want to prevent our spaceship from falling. So we will say tell the physics body of our hull to stop being dynamic. And what this means is that it won't be applied the gravitational pull. See there. Now we'll just run the actions as normal. It still has physics, and we're going to see why it still has physics in just a minute. Because what we want to do is that we want to create some rocks. We want a lot of rocks to fall down the screen, and when they hit the spaceship, they should bounce off it again to simulate collision detection and physics. So if we want to create more content to our scene, because if we want to make some rock nodes, then it is content, and thus it should be created in create scene contents. And here we create the spaceship node, which also created the lights. So we want to create rocks. and we are taking a different approach now. We are actually making an action, an SK action called make rocks, and that SK action should perform a sequence of actions, and one of these actions is to perform selector at rock on target self. So we are actually telling SK action to perform a selector called add rock, and the add rock method can be found on this scene itself. And then we are making another action, wait for duration with range. So wait for duration 010 with a range of 015. Let's just examine this for a bit. Here we call a method. That's all right. But what is this? Wait for duration with range. We've already seen the wait for duration, but this little with range, it actually randomizes the interval at which this wait for duration lasts. The wait for duration .10 here, it says that the average waiting time will be a tenth of a second, but it can range all the way up to 0.15. So this is the average waiting time, and this is the maximum waiting time of this particular wait for duration action. So each time that it performs this action, it's at a random interval, averaging this and max at this. But who do we want to call this action? I mean, usually we make nodes perform actions, so we make an action and then we tell the node to perform this action. But, well, we have a spaceship node, but we don't want the spaceship node to perform this action. No, we actually want the scene to perform this action. Whoops. Yeah. We want the scene to perform this action, so we can actually say SelfRun Action and then make a new action, so we can repeat the action forever. Make rocks. So the scene is actually a node. The scene is capable of running actions. It's not particularly a node, but it's able to run actions. So we're telling the scene to keep spawning rocks. That's that rock. Yeah. So now we want to implement this add rock method because we don't really have any. And in order to do that, we're going to do a little math. We are actually making a static inline CG float skrand f, and then we return rand divided with the CG float times rand max. There we go. And we made another static inline method or function, CG float skrand CG float low CG float high, and return skrand, and it's going to be empty. So we're using the other function that we just made above. We times it with the high minus the low plus the low. Zufügen zur Function call. Just to see here. Starting inline CG float skrand CG float low CG float high, return skrand skrand f. There we go. Yeah. These are two functions that we'll use to specify a random position of our rocks. Don't worry too much about these. You can make the spawning position of rocks in a lot of different ways, but these two functions here that uses each other is a good way of doing it. I'll show you in a sec just exactly where they'll spawn, and you can go ahead and use this in your own code if you want to. So we won't go into too much detail about that one, but what's more interesting is the addRock method. And it doesn't return anything because we want this to handle the creation of rocks itself. So we make a new sprite node, and we init it with a color. Color gray rocks, and they need a size, so CG size make 1010. So they aren't very big, but that's okay because they'll be spawning a lot of them. They'll be spawning an average 10 rocks a second. So we need to give it a position so it knows where to be on the screen. So CG point make, and we use our function SKRand. We pass in 0 as the first parameter and self dot size dot width as the second, and self size dot height -50. Yeah, and that is actually what gives our rock the random position by using these two functions that we made up here. And the rock.name, and remember, this is just for future reference. It has no effect on the node itself. It's just for our convenience, so we can work with it later on in another method. And we also need to, let's just separate this, because what we did up here, that's basic node creation. We've done this a lot of time. We make a new node with the color and size. We tell it to be at a certain position, and we give it a name. So what we want to do now is add physics to the node. And exactly as we did before, we just set the physics body property to be skPhysicsBody, body with rectangle of size, rock.size. And we want this physics body to be the entire rock itself as well. And we also want the physics body to use precise collision detection. And what that does is that it will be very careful to apply collision to all these rocks, because we have a lot of rocks here. So we need to set this property to yes. If we only had a few rocks, we didn't need this. But since we have a lot of rocks, we tell the physics simulation that you need to make sure to check for collision detection on all of these rocks. It's very important. So we tell it to do that. And then we add nodes to the scene. So self add child rock. And that's actually it. Let's just quickly go through what we did here. Let's just see. Create scene contents. We make a spaceship. And we told the spaceship to have physics, but not to be applied by that gravitational pull. And the reason why we're doing this is that it means that this spaceship will actually respond to collisions. If we didn't add this physics body to the spaceship, the rocks would just fall through it. But we did make it respond to collision detection, and we made some rocks by making an SKAction sequence repeat indefinitely on the scene that will perform a selector at a random interval called addRock. The addRock method will create a new sprite node, position it at a random position at the top of the screen, and give it a name. We added physics, and we specified that we want collision detection on all of the rocks applied precisely, and we added them to the scene. So let's go ahead and run this and see. So the doors open and the action should start. And look at that. You can see they hit the spaceship and they can remain there, or sometimes they bounce off, they hit each other and push each other off the side. And that's actually very, very great, because look at how much power we actually got from just a few lines of code. It's really amazing, and it saves you so much time when making games. If you didn't have physics simulation and you wanted to make it yourself, it would probably be inefficient and take a lot of time. And now it's of course easy to make a lot of changes. We could, if we go down here in the addRock, we could try and make them. We can make them green, green kryptonite rocks, and we could make them 30 times 30 in size. Let's just see that. There we go. You can see it's exactly the same behavior that we get, and because that we made the physics body be the entire rock size, we can just mess around with the size and the color, and the physics will just work in exactly the same way. And there's one more thing that we need to do in order to make this work properly, because if you check down here, you can see the node counts, and it looks to be pretty steady. We only made one draw call, and we are running at 60 frames per second, which is great. But if you let this run for a while, quite a while I might say, but if you let it run for a while, you'll actually see the frames per second start to drop. And that is actually because that this node count, it only shows how many nodes we currently have on the screen, on the scene here. So when these rocks, these nodes, they fall off the screen down here due to the gravitational pull, they will no longer count towards our node count, but they will still exist in memory, and the physics will actually still be applied to them. So even though you can't see them, they are actually still simulating collision detection and falling down the screen indefinitely. So right now we actually have a lot of rocks present in memory, but they don't consist of anything special, but and that's what enables us to run at a decent frames per second. But if you made a real game and you had them as images and with a lot of child nodes, your game would eventually slow down and potentially crash. So we need to fix this, and there's an easy way to fix it, because every time that our program has simulated physics, it will call this did simulate physics method on the scene. And what we want to do now is that we will remove rocks that are off screen, and what that means is that the y is less than 0. That means they are off screen, and we do that by saying self enumerate child nodes with name. We gave the rocks a name. We call them rock because kind of suited the needs here. So what this method does is that it will enumerate through each child node that has the name rock. So it will go through all our rocks that we've added as a child to the scene. And we use a block to do this, and the block needs to take an sknode node and a bool stop. We're not going to use the boolean value, but we are going to use this sknode node, and we make a bool stop because this method needs us to do so. Whoops. And the node sknode node here is what will hold a reference to each our rocks as we enumerate through them. So in order to work with them, we are going to use the node. So we say if node dot position dot y is less than 0. That means that if this particular rock has a position, a y position value that is less than 0, it means that it is off screen. So we want this node to be removed from the parent. Let's say on there. Yeah. And that's actually it. We go through all the rocks. We keep a reference using this passed in block parameter. And we say if the node's position is off screen, we remove it from the parent. And the second we remove it from the parent, there's no one that has a reference to this rock anymore. So automatic reference counting will automatically remove this rock now from memory and clean up the program. So even though we can't see any changes in our program, we made sure to clean up after ourselves, so that the only rocks we will ever have alive in memory are the rocks present on the screen. And that's very important to remember, that when you simulate physics and you ever have objects move off screen due to this gravitational pull, remember to remove them because they still do exist in memory. So if you ever have a program that spikes up in frames per second and you can't really figure out what's going on, it's probably because you've got to do some cleaning up after yourself. So I guess that's it, guys. Yeah, we actually made physics, we made collision detection pretty easily. It wasn't all too hard. So I suggest you go ahead and try it out and play around with it all you want to. And already now you're actually able to make a lot of cool games, or maybe not games. We haven't learned too much about user interaction yet, but you could, for instance, if we take the spaceship and we made it fill the entire screen, then the nodes or the rocks would actually stack on top of each other on top of the spaceship, and it could look kind of funny. It's hardly useful as a real game application, but it's funny anyways. So yeah, that's it for today, guys. I hope you liked it, and stay tuned for the next video. Thanks for watching. Remember to subscribe, and if you have any questions, go to my forum. And my forum is also a great place to keep track of my videos, because every time I make a new video, I post it on the forum with a link to the video. So you can always stay up to date with what I'm doing and watch the videos as soon as they become available. So yeah, thanks for watching, subscribe, check out the forum, throw a thumbs up or a thumbs down if you didn't like it, throw in a comment, let me know what you think and what I can do to improve. Thanks a lot, guys, and I'll see you guys next time.